Let's consider the age-old question of mass versus weight. As a spoiler alert, they're not the same thing. Please consider this question. To answer this, I want to point out pounds. Here we have 50 pounds of feathers and 50 pounds of lead. Pounds is a measurement of weight. Okay, in this case, if we have 50 pounds and 50 pounds, and that represents weight, then clearly they have the same weight. You'd be surprised how many people will miss this question though. It's usually when they answer something like feathers, they're usually imagining volume. So yeah, 50 pounds of feathers would be significantly more volume than 50 pounds of lead, but the question was about weight. Slightly different question. Consider this one. The key in this question is the word kilograms. So kilograms are a measure of mass. Here's where it starts to get tricky. If you didn't grow up in the United States, you probably use kilograms to represent weight all the time. In fact, a lot of the world does that. So why am I saying that kilograms is a measure of mass if a lot of people use it to represent weight? Well, that's sort of the problem that we're discussing here. Mass and weight are related, but they're actually not the same thing, and I'll try to justify that as we go. It does turn out, however, that they're connected, and if you have the same mass, and you're assuming both of these objects are on Earth, then you will have the same weight. So let's get into this. It's an important concept and one that is a common source of confusion. So let's start with mass. Mass is simply the amount of matter in an object. You can think of it as just the amount of stuff you have or an object has. We know now that Newton's second law tells us the net force on an object is equal to its mass times its acceleration. So if we rearrange that relationship a little bit, we know that acceleration is net force per mass. This relationship is useful because it shows the connection between mass and acceleration. Mass relates to the difficulty of accelerating an object. And if you look up in this relationship, so if you have more mass, then that's competing against the acceleration. They're canceling each other out. So more mass means you need more force to get the same amount of acceleration. Or you could think of it another way. If you have a fixed amount of force, then more mass is going to give you less acceleration. And so you kind of think of it like this. If you're trying to accelerate a large mass object, it's going to be difficult. You're going to have to apply more force to get the same result. Where here, if assuming this has a lot less mass, it's going to be noticeably easier to cause the same amount of acceleration. Okay, so this is the key to mass. You can think of it in some ways as, you know, that connection to acceleration. It's the more mass you have, the harder it is to accelerate an object. There is a standard for representing mass, and that is the kilogram. So what's interesting is when somebody from outside the US refers to their weight in kilograms, strictly speaking, they're referring to mass, although, you know, they're using it in a way that's the same as weight. And you'll find that in a lot of situations it's not really that important to distinguish. But for this video, I'll show some situations in which it's very important to distinguish between mass and weight. So let's explain weight. Weight, I'm going to define as a measure of how much an object is supported. Weight is usually the force on an object due to gravity, or what you could call the gravitational force. And you may have heard that before. In fact, I've sort of hinted at it in the past that you can pretty much treat weight as gravity. But strictly speaking, that's not true. And here's an example of why that would be confusing if it was equal to gravity. When somebody is falling, we often say they have a weightless feeling to them, or they're weightless. That's, you have those butterflies in your stomach because of it. Well, weightless doesn't make sense if we define weight as gravity, because the reason why they're falling is because of gravity. So there's plenty of gravity, but yet they're weightless. Well, that's why I think my first definition makes better sense, a measure of how much an object is supported. So in this case, the person is not supported by anything, therefore they're weightless. However, for most situations that we're going to consider, we can go ahead and think of weight and gravity as being connected, and we're going to define it as mass of an object multiplied by the acceleration due to gravity. That's going to be our weight. Now notice that G here, I didn't say gravity. Mass times gravity. That's not how it works, because otherwise, clearly how can weight be gravity if it's also mass times gravity, and the whole units get messed up and everything. So it's important to remember that G is not gravity, it's acceleration that's caused by gravity. That's a common mistake that a lot of people make when they're new in physics. So this is going to be our new definition that we'll use throughout the semester of weight. It's simpler just to write it as mg, so mass times the acceleration of gravity. So for example, if my guy here has a mass of 80 kilograms, what is his weight? Well, we just plug those values in. We know that on Earth, we have an acceleration of 10 meters per second squared. So when I multiply those together, I get 800. But when you combine kilograms and meters per second squared, that's what we call a Newton. So I've used this several times in the past. That unit is actually quite important. I want to highlight that. That unit hints at something crucial to distinguishing between weight and mass. So because weight has units of force, newtons we've always used to represent force, we can go ahead and say that weight is a force. On the other hand, mass is not a force. So there's a crucial difference right there. Here's some interesting thought experiments that I think will help emphasize the difference. Here I'm showing 3 astronomical objects. This is the planet Jupiter, this is Earth's moon, and of course Earth. Down here what I'm showing is the acceleration due to gravity at the surface on all of those objects. Okay, so if you compare, Earth is 10, the moon is 2, and I should mention that I've rounded these off, so these are just approximations. 2 compared to 10 means that the acceleration due to gravity is only 20% on the moon of what it is on Earth. So if you're falling, your speed would increase by 2 meters per second each second instead of 10 meters per second each second. Jupiter, on the other hand, is 26 meters per second squared, which means that it's a little more than 2.5 times more than Earth. So you would quickly fall if you happen to be there on Jupiter. The question I have, the experiment we're going to consider is, what if we imagine 3 identical 10-kilogram boxes and we place each one on the surface of these objects? And the reason why I have surface in quotations here is because technically there is no surface that we could land on for Jupiter. It's a cloud layer, but we'll just imagine that there's something that we could put right there. And I should also mention that nothing here is to scale. This isn't how they scale in real life. So with a box at each location, the question is, where is the mass the greatest? Why don't you think about that and pick an answer. key is the word mass itself. Notice I'm using kilograms to describe the boxes. Mass we defined as the amount of stuff in an object. So you can think of it as the total number of atoms that make up the object. But the idea is that that stuff is part of the object itself. So whether you're moving it from location to location, you're not actually changing the number of atoms or the amount of stuff that's inside of it. So in answer to this question, they're all equal. There is no greatest mass at any one of these locations. I've modified this question a little bit. Read through it and choose your answer this time. This time, the key is the word weight. We just defined weight as mass times the acceleration due to gravity. And I just mentioned that mass is the same for all three boxes in all three locations. But as we're showing here, the acceleration due to gravity is not the same. So if mass is the same, then this is the factor that's going to determine the answer to this question. So whichever one has the biggest g, which is of course Jupiter, that's going to be your biggest weight. So it's going to weigh almost a little more than 2.5 times more on Jupiter than it would on Earth, and over 10 times more than it would on the Moon. To me, this is where it gets interesting. Read through this question and pick your answer. The important thing to notice for this question is that I've replaced the unit to pounds, not kilograms. So what I'm describing by this 10 is a weight, and I even say that as a weight of 10 at their locations. And we just talked about how the weights aren't equal at the different locations. So it's tempting to go with this one here because you know that the weight is heavier on Jupiter, but that was for a specific amount of mass. The trick to understanding this question is realizing that the quantity that's varying between the three situations is mass. So to answer this, the Moon would be the location for the most amount of coins. So like if you were given a choice, which box do you want to pick, you definitely pick the one on the Moon. Remember that weight is mass times the acceleration due to gravity. If I have a fixed amount of weight, then this side of this equation is fixed. The bigger g is, that means the smaller mass is going to be to give us that fixed amount. So we want g to be the smallest to give us the biggest mass. So that's, the Moon would be the best option. Maybe I can show you like this. We know that mass times g is going to be our weight. In this example, we had a fixed weight of 10. That was 10 pounds, but I'm not going to use the units in this example. They'll actually just get in the way. So let's just say we have a weight of 10. In order to know how much mass we need, then we need to divide over g. So this is how we're going to determine how much mass is at each location. So let's do that for the Moon. So this is the mass on the Moon. So that's going to be 10 divided by, let me write that a little bit better, 10 divided by 2, and again we'll ignore the units just for clarity. So that's going to be 5. On Jupiter, we're going to have 10 divided by 26. That is equal to 0.38. All right, so you can see that the mass of gold that we would have on Jupiter is way less than we would get on the moon. So that's why we definitely take the box on the moon. As a final note, I want to go back to this slide that we saw previous. When I defined mass as the amount of matter in an object, and then I related it to the acceleration, I want you to notice, now that we've discussed about different locations in space and different gravities that are there, notice that in this relationship here, there's no discussion of gravity or acceleration due to gravity. It's just mass and force in order to cause an acceleration. So what that means is that if you go to Jupiter or you go to the moon, you might have, you will have different weights, but you still have the same amount of mass. And so what that means is to get the same amount of acceleration, you still need to apply the same net force. Remember that acceleration is the change in motion. So I'm not talking about just holding an object. Yes, it would be easier to just hold a heavy weight on the moon than it would be on Jupiter by far. But in terms of accelerating, think of like shaking the object back and forth. It's actually just as difficult because the relationship from Newton's second law doesn't have any consideration of gravity. So here's an example. Here we have a hammer thrower. He's going to spin that hammer around and throw it off. Let's watch.
Now Paweł Fidek of Poland. And great height. He likes it right out of the gate.
All right, if you ever tried to throw one of those things, that is really far. That's really impressive. So what's interesting is if he was doing this on the moon, he would actually feel the same amount of difficulty to get that thing spinning and to toss it off into the air. Because what he's doing is he's accelerating the object. So he's going to have to apply the same net force because it has the same mass. The big difference, though, will of course be once he lets go, because there's less gravity and basically no air resistance, it's going to go much, much further. And I think that about sums up the differences and similarities between mass and weight. And that's going to be the end of our video segments for Chapter 4.